Welcome back to Talk Universe. This is our show on the geysers of Mars and how you go about finding water. We hope you enjoyed the break. So there are a lot of questions about water on Mars, and one of the primary ones is where would it come from? Well, the answer to that is pretty simple. The same place the water on Earth came from. Terrestrial planets have a common heritage or lineage, if you will, in terms of how they formed and the materials that are used in their formation. Nature's pretty strict. The laws of physics and chemistry apply everywhere. One of the things we find is that volatile materials, molecules that evaporate easily and are the basis of organic molecules, those molecules are all over the universe, and water is one of them. Water is very important to planetary formation, and so when water ice sticks to grains of dust and little particles during the formation of a planet, it also allows itself to act as a sort of a glue to stick these particles together. But it also traps other molecules such as formaldehyde and methane and ammonia and carbon dioxide and carbon monoxide. So all of these materials become a part of the structure of any growing, accreting planet. So that's not really a big mystery, but it's something that a lot of planetary scientists haven't really fully explored, I think. One of the earliest planetary scientists I was aware of was George Wetherill, who did a lot of simulations on computers, the very first, in fact, that I'm aware of, showing how long it takes planets to form, the accretion of the particles. And he said it could range between 50 and 150 million years, and that's probably about right. Recent simulations seem to bear that out pretty well. It's in the tens of millions at the very minimum. Now, okay, let's talk about that. When we listen to scientists talking about how water got to the Earth, and we think that that would be the same for Mars, of course, a common answer is comets brought the water to Earth. That comets crashing into the early Earth during its formation would have brought all the water and formed the oceans, etc. That's an awful lot of comets, but okay, let's say that that's true. We've had a number of cometary and asteroid missions over the years. And one of the most striking things that those missions discovered is that comets tend to be incredibly dry. There is not, let's say, a ball of ice on the comet. And there are good reasons for this. I mean, yes, early on in the formation of the solar system, in its early history, there probably was a lot more ice because the sun, as you know, wasn't yet ignited. It wasn't giving off heat and light until well into the process of planetary formation. So this is something that a lot of people don't consider. And of course, a lot of people don't know this. So comets, as it turns out, are basically pretty dry and can't possibly be the source. And then recently, some asteroid missions were performed, and they too were found to be dry because scientists, some of them at least, went on, well, if it wasn't comets, maybe it was asteroids. A lot of asteroids hit the Earth, and yes, that's true. What they missed was the fact that the water is created inside magma. There is a complex chemistry that happens using volatile molecules and heated iron and metal, and it releases hydrogen and traps oxygen in the process and forms water. So anybody who has studied chemistry of hydrogen in physics classes has learned that you can take a corroded piece of copper, you can heat it up in a hydrogen atmosphere, and suddenly it becomes bright and shiny because the hydrogen reduces the oxides of the copper and leaves the pure metal behind. Well, what's involved in this process is that the hydrogen is joining the oxygen and forming water vapor, which is released. So if you were to take, let's say, malachite, which is a common ore of copper, grind it up into a fine powder, and this is a green semi-precious stone. In ancient times, it was found that they ground up malachite, mixed a little carbon powder with it from charcoal that they ground up, and some clean silica sand, beach sand. Put this all together in a crucible, and they'd make a clay oven, and they'd fire it up with some wood, and then they'd seal it. And what would happen is the heat of that clay would reduce the malachite into molten copper. Well, it's stealing the oxide out of the copper, and it's combining it with hydrogen, and it's converting it literally into water vapor. So a simple reduction would happen. Now, in the case of the furnace, the reduction was done by carbon. The ground up, the charcoal we grind to a powder, and the carbon would steal the oxygen and turn it into carbon dioxide. It's really the same process. Chemistry is a little different, but the end result is the same. So in this case, if you have no carbon, but you have hydrogen, then you steal the oxygen and turn it into water vapor. Very simple process. So what keeps the water on a planet? Why is Mars so dry? Well, first of all, it isn't so dry. The water is present, but the planet's presently in an ice age. And there are sheets of ice, glaciers of ice under the soil, sometimes only an inch or two underground. When the Phoenix lander landed in the north polar regions of Mars, on coming down, they used little rocket engines powered by hydrazine. And this rocket thruster actually sprayed down into the soil. And when it did, it melted some of that ice. And so they found mud and ice had been created in the landing, and droplets of water froze on the legs of the lander. They were imaged. And so when they took the digging arm out on Phoenix and started scraping into the soil, Phoenix's little arm revealed a very clear vein of ice, literally 2 inches under the soil. So it was landing on a sheet of ice all along. And if that ice were to melt, obviously, instead of a solid, you'd have liquid water. So the temperature of the planet is very important in keeping a liquid ocean, obviously. Three major factors, influence whether a planet's going to be wet, whether it's going to have a thick atmosphere. And atmosphere is everything here. If the atmosphere is too thin, then it's much more difficult for liquid water to exist. It boils off a little more readily. And so it narrows the range. On the Earth, we have a lot of ice at the polar regions, of course. And a lot of people have argued that, this would be a very bad thing for a planet if you're looking for life. But actually, the Arctic and Antarctic seas are some of the richest biospheres on our planet. Ice doesn't stand in the way. The reservoirs of liquid water are the most important thing. But the three factors, as I was saying, that really determine about a planet, its water, its ice, its atmosphere, are its gravitational field, the size of its core, and its distance from its star. Now let's talk about each of those briefly. Gravity on Mars is 38% of what we have on Earth. And what keeps the air around a planet? I mean, you've got this shell of air and atmosphere. Why doesn't it just blow off into the vacuum? Because after all, the vacuum isn't a boundary. It's not like there's a glass wall around your planet keeping the air in, not in the least. It's gravity. Each and every molecule of air is just like a ball or a stone. It falls to the ground. But there's a difference. Because the molecules of air don't weigh very much, temperature causes them to move. Temperature is velocity. And as they heat up, they would go from a liquid or a solid state into a gaseous state. And our atmosphere is a gas because the individual molecules are moving around at high speed. Well, speed is temperature from a physics standpoint. The hotter something is, the faster its particles are moving. Of course, in a solid, they're all bound together, and they just kind of all jiggle in place, but they're stuck, and they can't go anywhere. In liquid, they are stuck in a way, but they can't evaporate yet. But the most energetic ones do evaporate and become vapor or a gas. So atmosphere is, think of it literally as trillions upon trillions of frictionless superballs bouncing around because they're hot. Nothing is holding them in except gravity. Gravity is keeping the atmosphere around the planet. So this comes to the next point. If your gravity is low, it's much easier for a particle to escape into space. And the heat of the sun will do that. It will heat up air molecules, and the most massive ones now will not have the energy to escape orbital velocity or escape velocity and get away from the planet into space. However, the lighter ones, hydrogen's lost very easily. Light molecules do blow off into space. And for water molecules, what can happen is a water molecule at the top of your atmosphere is struck by ultraviolet. It splits into hydrogen and oxygen. The hydrogen is lost, the oxygen may stay, but eventually it's consumed by geological processes. It oxidizes metals or minerals, and so it's locked up and it's not an atmosphere. It's part of a mineral now. So the hydrogen being lost is a big thing. And hydrogen loss is one of the major things. It takes oxygen, leaves oxygen behind, but it takes water out of the environment. Mars also has another problem, and its core is very small. So consider that on the Earth, the size of the core means that it generates a lot of heat and volcanic activity continues. And this means that outgassing of materials from inside our planet are constantly replacing our oceans and atmosphere. Water vapor accounts for roughly 90% of what comes out of a volcano. You see all the smoke, and it really isn't. It's steam loaded with particles of dust and dirt. So all of that, most part of it, all of that ends up in the ocean or in the lakes or in the rainfall. And the rest of the material either falls to the ground or ends up in the atmosphere and gets processed by organisms and biology and becomes a part of our air. We don't see this happening on Mars because its core is very small, and while there may be some geological activity from the heat inside the planet, it really isn't that great. We don't have a huge load of heat energy available to keep the atmosphere renewed and the oceans renewed. But again, remember, it's an ice age. The ice is still there, it's just frozen. So heating the planet would go a very long way toward returning the oceans and the atmospheric pressure. Let me remark on the fact that a great deal of the white-looking ice you see at the polar caps, it's really dry ice, carbon dioxide. And if that were to sublimate away and become part of the atmospheric pressure would go up, making it easier for water to remain in a liquid state. And it also would trap a lot more heat from greenhouse effects, so the planet would warm up. And you end up with this being a snowball effect where it becomes more and more global warming, more thickening the atmosphere, more ice melting, oceans returning, and it goes cyclically just like the ice ages do on the Earth. So this is a process that could easily set the planet into a biological renaissance that could return to its ability to support water and life and thicker atmosphere quite easily. Some people have suggested we could nuke the planet and warm it up and vaporize some water and some CO2, and that's a silly idea. Yeah, it could work, but there's something much easier you can do. You take carbon black powder and you dust the polar caps, and you dust the soil where you see glaciers. And in a very short period of time, the heat of the sun, which is roughly 500 or 600 watts per square meter on Mars, solar energy itself would take the process and run with it, and you could just step back and it would happen. And what's cool about this, that carbon could very likely be consumed by organisms, or the particles could wash under the soil, and that would end the warming process, and the atmosphere and the water would reach thicker proportions, more available proportions. We'd see the seas return, and possibly some of those organisms might be in stasis, like brine shrimp or tardigrades, and they would emerge and biology would begin again. I think that's a very interesting prospect and something that we could do quite easily. Solar distance. Why is distance from the sun so important? Well, yes, obviously the heat factor to keep a liquid ocean. But here's something that a lot of people aren't aware of. When an air molecule reaches the top of the atmosphere, what heats it up? Heating effects from light is literally absorbing the momentum from the light and speeding up the particle's movement. That's what heating is all about there. And if an air molecule, which already has the ability to reach the top of an atmosphere, is moving around at the edge of space, and it gets smacked by solar wind or a little bit of sunlight and reaches a high enough velocity, it literally can blow off into space, just like a little spacecraft leaving the planet on a permanent journey. So sunlight does erode an atmosphere. It does blow it away. Lighter atoms first, heavier atoms left behind. Consider Venus. Venus lost all of its water. There may be some still inside the planet, but that's of no consequence at this time. But the carbon dioxide molecules, which are quite dense, are the ones that are left behind. So Venus' atmosphere is almost entirely carbon dioxide. And take note of the fact the same is true for Mars. So this is an interesting theme. Mars lost its water, mostly to space, but a large part of it is still available in glaciers just under the surface, and we know how to warm the planet up, unlock that, and release it. I think it would be a worthwhile project. I'm Charles Schultz. This is Talk Universe, and we'll be right back shortly.